Hello, this is the second part of the video lecture for chapter 24. During the first part, we covered flux, the concept of the flux. And in this video lecture, this part, we will be covering Gauss's law. Gauss's law depends on the concept of the flux. And as we said in previous lecture, Gauss's law allows you to calculate the electric field due to a distribution of charge that is highly symmetric. Okay, specifically, it's highly symmetric. Let me go back to the note. So Gauss's law. The mathematical statement of Gauss's law says that the surface integral, and we insist that this surface have to be closed surface, so that's why I put the circle here. The surface integral of E dot dA, I'll put it in vector form, is equal to the charge enclosed over epsilon naught. This is the mathematical statement of Gauss's law. I'm going to explain it to you right now. I'm going to take a very simple example. Let's say, for example, you have a point charge. Let's say here. And I would like to know the electric field of a point charge at a distance r at this point. Let's call it point P. As you know, we have done that in the previous chapter. We said that the electric field due to a point charge is basically 1 over 4 pi epsilon naught q over r squared, correct? And the direction of the electric field is going to be something like that, in the radial direction, right? We already done that. And we were able to get this result using Coulomb's law. Okay? Now, what I want to do, I want to use this fancy equation right here to calculate the electric field due to a point charge at a distance r. I'm going to do the same thing, okay? And I want to see if I get the same result. Got it? Okay. Here is how you do it. Watch. So, here is my point charge. Okay? The first thing you need to do is that you have to create a Gaussian surface, because here you're taking a surface integral, okay? And this surface integral is what we refer to as a Gaussian surface. What does that mean? Look at the distribution. If you have a charge, any distribution of charge, say this point charge that you're looking at, what is the shape of the electric field? How does it look like, the whole electric field? Well, the electric field is going to look like this. And the shape of it really is a spherical shape. You see what I'm saying? I mean, it is coming out of the charge in the radial direction in all directions, right? And it has that spherical shape to it. However, if I have a line of charge, say I have a thin line of charge like that, let's make it positive as well, like this. And so what you will have, you'll have the electric field lines coming out of it. It will have this cylindrical shape to it. You agree with me on that? So those kind of shapes we refer to them as Gaussian surface. Okay. So what I'm trying to say is this: if I have a charge, positive charge, let's say, the one I'm going back to the charge that I'm talking about, and I want to calculate the electric field, let's say at this point right here. Okay. Right here, at the distance r away from it. Okay, what I will do is that I would create a Gaussian surface where this, remember, this Gaussian surface is an imaginary surface, where this Gaussian surface passes through this charge. Here it is. You know what? Let me do it the other way around. It's kind of hard to draw. Here is the Gaussian surface right here. And I'm trying to find the point. This is the point r at the distance r. See what I'm saying? There we go. So now if I ask the question, remember we call that what? Gaussian surface. Okay, now what is the direction of the electric field at the Gaussian surface? Well, it's outward. And what about it here? It's outward. See that? And here, it's outward, and so on. Remember, it's a Gaussian sphere, and therefore, or it's a sphere, and therefore the electric field here, here, and here, and here is basically the same. You got that? Okay. Now, I use Gauss's law. So it says that the surface integral of E dot dA is equal to, let's forget about the vectors for now, is equal to the charge enclosed over epsilon naught. Okay? Now, we just said if this is the Gaussian surface, and we said that the electric field out of the Gaussian surface are all the same, in other words, they are all constant. Make sense? They're all constant. They're not different. And therefore, this E in this integral is constant, and therefore I can safely kick it out of the integral. You see the trick? So I can kick it out of the integral, and what I'm left with is the surface integral of dA equals the charge enclosed over epsilon naught. Now, what is this one? What does this mean? The surface integral dA, what does that mean? It basically means what is the surface area of the Gaussian surface. That's really the meaning of it, mathematically. Surface area of the Gaussian surface that I'm basically studying. Which is this one right here for our case. Well, what is the area? What is the surface area of the sphere? The surface area of the sphere is 4 pi r squared. Go back to your geometry book. That's the surface area of the sphere. Okay? Not volume, not the area of the circle. The surface area of the sphere is 4 pi r squared. In other words, I really don't need to carry any integral. As a matter of fact, most of the time you don't. Okay? We carry integral if you take an advanced course in electricity and magnetism, or the actual. But for our course, it's a sophomore level course, 99% of the time you're not going to carry any, you're not going to do any integration. You basically make this simple argument where, well, this is nothing but the surface area of whatever Gaussian surface I'm dealing with. We happen to have a sphere. It could have been a cylinder. It could have been something else. You see what I'm saying? So anyway, so if we know that, therefore, if this is the surface area of the Gaussian surface, which is nothing but 4 pi r, r squared, excuse me. So in this case, the left-hand side of the equation becomes, excuse me, is equal to E times 4 pi r squared equals charge enclosed over epsilon naught. And now I'm done. All I need to do now is to solve for E. So solve for E, move this to the other side. So it's going to be Q enclosed. What is the Q enclosed? It's basically this Q right here. This is enclosed. Enclosed where? Enclosed within, inside the Gaussian surface, divided by 4 pi epsilon naught r squared. And as you can see, we arrive at exactly the same form as Coulomb's law right there. 1 over 4 pi epsilon naught Q over r squared, and we got it exactly the same way. Okay, but we did it in a kind of an elegant way. You see what I'm saying? Okay. Now let's take a tougher problem. I mean, this is not the purpose of Gaussian. Gauss's law is to do a simple problem like that. The purpose of it is to do a little bit harder problem. Again, we're not going to be doing any tough problem, really. We're just going to be picking specific ones. Let me take another one. Let's say, for example, before I do that, I want to show you something interesting. It's not mentioned in your book when it comes to calculating using Gauss's laws to solve problems, and that is the following. You will come across two kinds of charged bodies. One, it can be insulating, and the other one is conducting. Okay, so when you read a problem, you may read something like a non-conducting sphere or a conducting sphere. Okay, in other words, one is metallic, made out of metal, and the other one maybe made out of plastic or wood or whatever. Okay, and so therefore it's not it's insulating in that case. So conducting, non-conducting, or conducting or insulating rather, either of those words, you need to know they have a lot of meanings to them when it comes to applying Gauss's law. Here is the meaning of them. So when you read the word insulating, such as insulating sphere, for example, okay, what that means is the following. If I have a sphere that is insulating or non-conducting sphere, the charge on that sphere will be uniformly distributed all through the sphere. This is very important. Keep that in mind. You may want to write it down in your notes. So it is uniformly distributed all through the sphere. So here we say charge is distributed throughout, let's say, the sphere. Okay? In other words, what that means is that if the radius of this sphere is, let's say, big R, and any radius inside, we'll call it small r, so E, the electric field, does not equal to 0 for r less than big R. In other words, E does not equal 0 inside the sphere. That's what I'm trying to say. Okay? Only for what? Insulating sphere or non-conducting sphere. However, if you read a word such as conducting sphere, or conducting cylinder, conducting whatever, conducting sphere, in this case you have a conductor, what will happen is that the charge will accumulate only on the surface. There are no charges inside the sphere. It will look something like that. Here is the sphere, and I go and charge it of radius big R, and what will happen, the charges will accumulate only on the surface. I'm talking about a solid sphere though, okay? And there is no charge inside, okay? There is no, I'm using my mouse here, there's no charge inside here. The charge is only distributed on the surface. So here, charges accumulates at surface. And in this case, the electric field inside is equal 0 for r less than r, or E equals 0 inside. You see what I'm saying? Okay, this is very, very important. We'll come back to it in a minute. So let's say, for example, here's an example. That's an example just for my lectures, for my lecture note, that is. Let's say I have a conducting sphere of charge. Let's make it big Q, okay? And find the electric field inside and outside the sphere. Of course, we're going to be using Gauss's law. This is a simple problem. Okay, we haven't done the hard one yet. Okay, so here he said, I have a conducting sphere. Okay, and the word conducting, you always pay attention to it. Of charge big Q. This is the total charge on the sphere. We want to find the electric field inside and outside the sphere. What does that mean? It means this. Here is the picture of the sphere. I'll make it a little bit bigger. Okay, and it's a conducting sphere. Assume it's solid, or doesn't have to be a spherical shell. Maybe it's a solid sphere. Since he said the word conducting, it means the charges are going to accumulate on the surface like that. And now he's asking for what is the electric field inside and outside. Well, let's do inside first. And inside, what I will do, I will write it this way, R less than R. For a good reason, I'll show you why I use this symbolism. Now, we just said that, maybe I forgot to mention, let's assume that the radius of the sphere is big R. Okay, that's the actual radius of the sphere. And remember Gauss's law. Let me put it here on the side. It says E dot dA equals charge enclosed over epsilon naught. Okay? Okay. Again, before you use the left-hand side of Gauss's law, you have to have a Gaussian surface. Okay? So when he says find the electric field inside, well, that means I'm going to have to construct a Gaussian surface inside. With what radius? Any radius you want. We're going to call it small r. So the small r here is a variable, remember. The big R is a constant, a number, say 5. But the small r is a variable, like x, y, and z. It's a variable, and it is the radius of the Gaussian sphere, okay? This is the symbolism that we use here in our book. So the small r is a variable, and this is the radius of the Gaussian sphere. So what I want to do for inside, first thing I need to do, I'm going to create the Gaussian surface. Again, it's the radius of that surface is arbitrary. You pick any surface, any radius you want. So here it is. I always put it in dotted, in dotted lines, so you can contrast it with the solid line, which is the actual sphere, like here. This is the actual sphere, thus the Gaussian surface is dotted, okay? And of course, the radius of the Gaussian surface is small letter r. You got that? Okay. Now, I apply Gauss's law. I mean, I already told you that the electric field is 0, but I'm going to show you why. I'm going to show you right there. I'm going to prove it to you why it is 0. Okay, so I'm going to use Gauss's law. So it says the surface integral of E dot dA is equal to Q enclosed over epsilon naught. Okay, I forgot to mention here, the total charge on the sphere is big Q, he said, right? In the problem right there, he said a conducting sphere of charge big Q. So I just want to put the Q here. Okay, now let's work on the left-hand side, at least the first step. Obviously, if there is an electric field here, that electric field is going to be constant because it has a spherical symmetry. And sorry, the sphere is not terribly centered, but anyway. So it has a spherical symmetry, and therefore the electric field at any point on the surface of the Gaussian surface will be constant, and therefore I can safely kick it out of the integral. Again, this is the case for most of the problem that we do in this course. So the E here comes out, so I'm left with, we have E, and then the integral of dA equals charge enclosed over epsilon naught. So far so good? Okay, now what is that? Again, we said that the meaning of this one, the surface integral dA, is nothing but the surface area of the sphere, which we already know what it is, 4 pi r squared. R being this r, and 4 pi r squared is basically the surface area of this Gaussian surface. Got it? So it's going to be E times 4 pi r squared equals to what? The charge enclosed. What does that mean? It basically, what that means is the following. You look, here is the Gaussian surface. Now look inside the Gaussian surface and ask, what is the value of the charge here? Do you see any charges there? No. The charges are outside here, big Q. But inside here, there are no charges. In other words, there is no charge enclosed. That's E and C is enclosed. Your book doesn't use it. He uses IN, inside. I like enclosed. So there are no charges inside the Gaussian surface, as you can see, and therefore this is 0. And what does that mean? So therefore, the electric field is equal to 0 inside, for R less than R inside. And we have just proven why this relationship holds. You may not, it may have been vague for you, but now we have just proven why this is correct. You got that? Simple? Okay. Now, the next part of the question He said the conducting sphere of charge Q, find the electric field inside and outside. Okay, we did the inside. The electric field is 0. Okay, now outside, which means R greater than big R. Again, the small r is what? The radius of the Gaussian surface. Got it? Okay. So what I'm going to do, let me redraw the same sphere that we're dealing with. Here it is. And we have, it's a conducting sphere, so the charges accumulate on the surface. And the big charge here is Q, radius of the sphere is big R. Okay? And the first thing I need to do, I need to draw a Gaussian surface. And the Gaussian surface in this case is going to be outside. Because he said find it outside, so it's going to be outside. So here it is. There we go. Of radius what? R. Small r. See what I'm saying? There we go. That's radius r. Okay. Apply Gauss's law. Let's work on the left-hand side. We make the same argument. We have electric field coming out of it like that, right? And those electric fields are constant. They're exactly the same. That means I can take this E and kick it out of the integral because it's a constant. So I'm left, same thing, same argument over and over again. And that's going to be dA, charge enclosed over epsilon naught. And this one is nothing but the surface area excuse me, of the Gaussian surface. So that's going to be E times 4 pi r squared and Q enclosed over epsilon naught. Now, if you are standing on the Gaussian surface right here and you look inside and you ask, what is the enclosed charge? Well, it's big Q. See what I'm saying? There we go. So I can replace the Q enclosed right here with big Q. So that's going to be E equals to 1 over 4 pi epsilon naught big Q over r squared. And we arrive at the electric field outside. This is for outside. Got it? Okay. Now look at this equation. Does it look familiar to you? I hope it does. Because if you remember, from Coulomb's law and Gauss's law covered today, if you have a point charge, Q, and I want to find the electric field here, I just draw a Gaussian surface around it. And when we do Gauss's law, we arrived at exactly the same thing. Exactly the same as that. Now, what does that mean? What does that tell us? What it tells us is the following. Whether you have a sphere or a point charge, if you're going to calculate the electric field outside that body, regardless of its shape, is going to behave like a point charge. That's basically what it says. Regardless of its radius, it's going to behave like a point charge. Do you see what I'm saying? That's basically what it says. So as you can see here, this sphere behaves like a point charge. Because they got the same form, as you can see. Exactly the same form. There's no difference whatsoever. Okay? All right. Here's a tough one. And this is an extremely popular problem. You'll find it in just about every physics book. And every student who have taken this course for the last 100 years have probably done this problem. It's a very, very famous problem. So pay attention to it. Very, very important problem. And it's about basically the same problem that we have just covered, except that we're going to replace the conducting sphere with an insulating sphere. Okay? And it's covered in a book. Let me look it up for you, so you can basically go back to it. The one I just covered, guys, it's very similar to example, forgot to mention that, but that's just for my notes. It's this one here is also example 24.3. Okay, forgot to mention that, but it's the same problem. He does it basically the same way I did it. And then the interesting one is 24.4. So you can go, let me show it to you in the book. Let me just put it down here. Very important problem. 24.4. And it's section, I need to know the section in order for me to get to the book. 24.5, okay? Let's go to the book. Uh, 24.5. Okay, this is the example that I have just done, okay? I think, yeah. Outside the sphere, this is the one I've just done. This is the Gaussian surface, which is this brown color. I put a dotted line, but anyway, he got a fancier way of writing it, of drawing it. And then example, whoops, I went a little bit further. Yeah, I want to do also example 24.5. I'm going to do that as well. But I want to do example 4. There it is. I'm just going to read it for you, and then I'm going to do it my way. Okay, he said, what is the electric field inside a uniformly charged sphere? Should be insulating. 24. He didn't mention that. Inside. We will assume, I'm sorry, hold on. I mean, he does assume in the solution it's insulating. He didn't mention it here. But anyway, it's an insulating sphere. Okay. Let me show you how to do it. So what we have is the following. I have a sphere. Again, it's a non-conducting insulating sphere, and therefore the charges are uniformly distributed all through the sphere. Okay? So it looks something like that. Here is the insulating sphere. And I have charges all over, distributed uniformly all through, like that. Okay? Again, the radius of the sphere will make it big R. Okay, before I do this problem, if I ask you the question, what is the electric field of this insulating? Oh, I forgot to mention, let's assume that the total charge on the insulating sphere is big Q again. All right? So, what is the electric field for R larger than R? In other words, if I take this insulating sphere, here it is, I'll make it a little bit smaller, okay, and we charge big Q, and here is my Gaussian surface, and here is the radius small r, that's the radius big R right here, right? So as you can see, it really doesn't matter whether it is insulating or conducting, you're going to get the same answer, this. See, if you apply it, charge enclosed over epsilon naught, and whether it's insulating or not, the charge enclosed will basically be big Q, and this is basically E4 pi R squared. It really won't matter. You see what I'm saying? So you're still going to get the same answer over point charge. In other words, whether the sphere is insulating or conducting or a point charge, as long as it's outside, the Gaussian surface is outside, you're going to get the same expression, basically. Okay, it will behave like a point charge. That's basically the moral of the story, is that it's going to behave like a point charge. The interesting part becomes, or the hard part, is when what is the value of the electric field inside? Well, if it's a conducting, it's 0. We have just proved that. Now, what about if it's insulating? This is where the difficulty comes in. Pay attention. I'm going to draw the sphere again. This time I'm going to make it a little bit big. So here for inside, R less than, big R less than. So R less than big R, so that's inside. Okay, here is the sphere. Do it again. If I don't think about it, I make a nice circle. I have a nice steady hand today for some reason. Anyway, so here it is. I'm just going to put little pluses here and there. There they are. And of course, the radius here is big R. I'll come back to it. Okay, so what I want to do is I want to create a Gaussian surface inside. Let me put it in a different color. I'll put it in pink. How about that? So here is the center right here. Oops, that's not what I wanted. That's kind of a highlighter or something. I don't know what it. I don't want this one. Go back to, I think it was okay. All right, let's try this one. So in this case, I'm going to have, here is the Gaussian surface. Is that okay? And this is the radius r, small r. Okay. Now remember, let me go back. Remember, we said that the total charge on it is big Q. Do you see the problem now? You can pause the video and think about it. Here is what the problem is. This big Q describes all the charges all throughout the sphere. But since I'm taking a Gaussian surface inside, so the Q here is really a fraction of this big Q. You see what I'm saying? And the larger the Gaussian surface inside, the more big Q I can get. So I need to find a way to describe how much charge there is inside the Gaussian surface. But I hope you see the problem here, is that there is a fraction of the charge Q here, not the whole charge. You see what I'm saying? So how do I do that? How does that work? Well, here is how it works. Watch. Here is where, remember we covered charge density. We said that, if you remember, let me review them very quickly. We said that the charge density rho is equal to Q over V, correct? That's for volume, if you're dealing with volume. And we said that the area charge density, sigma, is Q over area. That's for area. And then we have a linear charge density, lambda, and that's equal to Q over the length. Remember that? Okay. Those are going to come in really handy. Let me show you how. Let me write them in terms of Q. So it becomes Q is equal to rho V, and I'm talking specifically about the volume, because here, this problem right here, it deals with volume. So I'm going to talk about this one. Now, do you agree with me? Let's say, before I solve this problem, let me just I'll show you something different. Let's say I have a block of lead, okay? A big block of lead. Let's say 1 foot by 1 foot by 1 foot. Okay, so that's 1 foot by 1 foot of lead. Okay, and the density of it is, let's say, rho naught, whatever it is. Okay, now if I take a chunk of it, let's say just a small chunk, like this much, a small cube of it, this cube right here, I take of it right there, I take that thing right here, I cut it out. Okay, obviously the mass of the small cube is less than the mass of the big cube, and the volume of the small cube is much less than the volume of the big cube. However, the density of it will still be rho naught. Make sense? Now, rho here is the density. I'm not talking about charge density. I'm talking just a regular mass density, material density. And we know that material density, rho, is mass over volume, right? So if the mass of this big cube is big M, and its volume, let's make it big V, okay? And then here, the mass of this thing is small m, and the volume is, say, small v, rho naught will also be equal to big M over big V, and it's also equal to small m over small v. This makes sense? I hope you believe that, because it's a ratio. See, the density has nothing to do with it because it's a ratio. You got that? So the density is the same. Well, I have the same concept here, and that's what's going to save me to solve this problem. Here's how it works. Watch. So Gauss's law says the integral of E dot dA equals to the charge enclosed divided by epsilon naught. Now let me look at the charge enclosed here. Right here, the charge enclosed is basically this within the pink Gaussian surface. That charge enclosed is less than big Q. It's a fraction of it. It's part of it. It's like this small m is part of this big M. Or this small v is part of this big B. You get that? Okay. Well, by definition, here it is. By definition, see, we have the charge density rho is equal to Q over V. So as far as the Q naught is concerned, so that will be Q naught, I'm sorry, Q enclosed, I'm sorry, we're calling it Q enclosed, I'm confusing things here. So as far as the enclosed charge is concerned, so that's going to be Q enclosed over the volume of the Gaussian surface. Well, what is the volume of the Gaussian surface? What's the volume of the sphere? 4/3 pi r cubed, if you remember. 4/3 pi r cubed, the volume of the sphere. So rho here is, that is generally the generic formula for it is Q over V, charge per unit volume. Well, if I apply it only for the volume of the Gaussian sphere, it's going to be Q enclosed over the volume of that Gaussian sphere, which is 4/3 pi r cubed, where r here is the radius of the Gaussian surface. Also, watch this. This charge density is equal to big Q over big V. Remember, let's call that V prime, sorry, okay? This big V, however, is the volume, the entire volume of this sphere. See, that is the big Q, and that is the associated volume of the big sphere. So that means this big Q over big V is big Q over 4/3 pi big R cubed. Remember we said that the radius of it is big R. Do you see that so far? Why am I doing all of that? I'm doing this because if I equate those together, I am going to get a ratio of what is Q enclosed in terms of big Q. It's a really smart move. Okay? So let me equate them together because those two charge densities are the same. Now equating them together, this will give me Q enclosed over 4/3 pi r cubed is equal to big Q over 4/3 pi big R cubed. The pi's cancel out, 4/3 cancel out, and I'm going to solve for Q enclosed because this is the one I'm interested in. I want to know how much charge enclosed within the Gaussian surface, and that will give me big Q R cubed over big R cubed. And there we go. I have a really cool looking expression for the enclosed charge. So far so good? All right, this is the hardest part of this problem. This is if you understand that, the rest is easy. Now, remember, let me just go back, and he said, in case you forgot, we're trying to find the electric field inside the insulating or non-conducting sphere, right? So here it is. Let's go apply Gauss's law. Gauss's law says the integral, I'm a little bit ahead of myself. The integral of E dot dA equals Q enclosed over epsilon naught. Well, again, we make the argument the electric field is a constant, therefore I can kick it out. And so I have the integral of dA equals Q enclosed over epsilon naught. And of course, this one is nothing but what? The surface area of the Gaussian sphere. and that would be E, and that's equal to times 4 pi r squared equals to what? Equals to Q enclosed. Well, what is Q enclosed equal to? There we go. That's the one we're going to put in here. You see that? So now I have Q r cubed over epsilon naught big R cubed. Clean it up a little bit. Move this to the other side. So I have E equal to 1 over 4 pi epsilon naught big Q, and watch this r squared and r cubed reduce, and you end up with big Q over r cubed times 1 over r. Oops, I'm sorry. I know it doesn't look right. Times r. I'm trying to do it in one step. Is that right? I move this over here. Becomes that. Yeah. And there we go. We have this formula. Looks really different. We've never seen a formula like this before. So this is for r less than big R inside. Okay. Now remember, for r outside, it's just going to behave like a point charge, remember? And we said it's going to be equal to what? 1 over 4 pi epsilon naught Q over r squared, correct? There we go. Okay. Now one more thing I want to talk about that. Look at those two. Expression. One for the same sphere. I mean, those are two expressions depict or describe the electric field of one of that insulating non-conducting sphere inside and outside. Okay? And as you can see, they're very, very different. Now, here is the thing. Imagine I want to try to graph them. Now remember, look at this. I want to make a graph of both of them. Look at this. Again, let me put it in a different color so you can see it better. How about green? Look at that. See this part right here? It's all constant. This is the radius of the sphere, big R, just a constant. The sphere is not changing. And that's Q. The charge is not changing as well. And everything here is constant. And then this whole thing is also a constant. So the variable here is just R, and the variable here is 1 over R squared. In other words, this function here is a linear function where this represents the what? The slope, correct? Where here it is kind of it's not really it's a curve, okay? If I'm going to try to graph it, and I'm going to graph both of them on one curve, in one graph, here's how it looks like. It's going to look something like that. This is interesting. Okay, remember this is inside, so we're starting from radius 0 all the way to R, and then in this one we are starting from big R all the way to some arbitrary value R. You see what I'm saying? Make sense? Okay. So this one inside, the electric field is linear. I'll come back to what that means in a second. But it's linear, as you can see. So when this is the slope, it tells you how steep the line is. Let's assume the steepness of the line is this way. There it is. All the way up until I get to R. This is the electric field. Okay? And this one, I have unusually steady hand today. I don't know why. Usually I can't draw horizontal lines like that. Anyway, here we go. I'm happy about that. And here, however, it's 1 over x squared. How do you graph 1 over x squared? Use your graphing calculator and look at it. It's going to look something like that. I hope I have that same steady hand. It's going to look a curve like this that is asymptotic. I'm trying to make it asymptotic. There we go. Something like, it's a curve, guys. It's a curve, smooth curve. I think you have, your book has it. Let me show you how your book looks. Have it. There it is right here. See that? This one probably looks a little bit better than mine. Oh, that's the maximum. Okay, there it is. So as you can see, it's linear, and then it's a curving path like that. You see what I'm saying? That's 1 over r squared, and this is r. And then right here, this is the radius. This is the cutoff. This is right at the surface. And of course, this one here is the value of E at the surface. Well, what is it equal to? Well, they're both equal. In other words, this expression and this expression are both equal at the surface. So if you plug in big R in either of them, you will get the same answer. Okay, so basically it's going to look something like that. Q over r squared, basically. That's how it looks like right on the surface. Okay, so let's see, what's the meaning of that? Well, look at it. If what that means is this. Here is the surface, the sphere that we're talking about, and it's a non-conducting sphere. So if I am walking, let's assume that I'm walking from inside the sphere to the outside. Here I am, again, figuratively speaking. I'm walking, and I am with my some detector that detects charges, or electric field intensity, okay? And I'm walking from the center of the sphere all the way to the outside. What I'm going to notice is the following. As I go further and further, closer to the surface, let me use my mouse so you can see the green circle. So I'm starting here. As I go further and further away from the center toward the surface, look at the graph. What's going to happen is that the electric field will increase, the intensity of the electric field will increase linearly with R, okay? And it's going to reach a maximum value right at the surface. And what's going to happen after that? Bam, it's going to drop as an inverse square law. Is that right? Here it is. It's going to drop as an inverse as I go. So as I walk further away from it, say I'm here now, and I'm walking further away from it, it's going to drop as an inverse square law. And if I am really far away, it's just going to attenuate to 0. It's asymptotic. It's just an asymptotic function. Okay? So what, in other words, the field will get more intense as you get further from the center. Okay? There we go. See? Linearly until it reaches the surface, then it's going to drop down as an inverse square law until it reaches 0. Okay? Very interesting way of looking at it. So, anyway, so one more problem I want to work on. I have at least, let's see, 2 more examples, and then 2 more or 1 problem from the homework. Okay, the next example is 24.5. Here we have a little bit of a different creature, a distribution of charge, that is. Here we have electric field of a long charged wire. So what you have is this, I don't know if he has a picture of it or not. There it is. I'm going to draw a better one. That's example 24.5. So what I have in here is a line of charge. Imagine a line of charge, and let's assume that this line of charge is infinite. And when we say infinite, it means very long, okay? It's not a mathematical, in the physical world, there is no such thing as infinity. But when we say infinite, it means it's very, very long. Or very, you see what I'm saying? Okay, so I have a line of charge. Let's say you have a wire. Try to make it as thin as possible. Here it is. Again, we'll assume it extends from both sides, say miles and miles, let's say, okay? And let's assume hypothetically that it is positive, like that. and I want to know, find the electric field. Get away, due to an infinite line of charge. Okay, of course, when we say line of charge, that means the line is infinitesimally thin, so we don't talk about inside, that it doesn't have a radius, so the radius is totally negligible, okay? So now when you look at it and you look at the distribution of the electric field vectors, the vector field coming out of it, which shape does it take? I hope you believe it is cylindrical. Okay, so in this case, it has a cylindrical symmetry to it. In other words, if I'm going to draw a Gaussian surface that is suitable for this line of charge, it's going to be that has a cylindrical symmetry. All right. So what I want to do, I want to draw a finite cylindrical Gaussian surface. Finite. Remember, this is infinite. Finite. Now you may ask, well, what about the rest of the wire that is not included within the Gaussian surface? Well, hold on a minute. We'll see. You'll see what there's a little trick to it that actually works pretty cool. So here is, I'm going to just draw a finite cylindrical surface. Here it is. Again, I could have done it in dotted. I can dot it. There we go. Just a dotted thing. Just like that. And it will actually works fine. And let's assume that this cylinder, this cylindrical Gaussian surface, has a length L, for example. And of course, the electric field is going to be coming out of it symmetrically like that in all direction. And all these E's are equal to each other. I hope you believe that. Right? All right, great. And of course, the radius of it is small r. Remember, a small r indicates a variable r. Okay? So now I want to apply my Gauss's law, the formula. Before I do that, let me show you something else. So if I take one of those, let me just take this. There we go. If I take a small portion, you know, an element of area here, so the electric field is going to be going like that, and then this is the differential area, dA. You see what I'm saying? And of course, you integrate over those two, E dot dA, you know, just like the Gauss's law, and that will give you the due to the entire sphere, assuming the entire cylinder. So anyway, here is Gauss's law. The charge enclosed over epsilon naught. Now, this one here, the left-hand side of it, remember, it's no longer a sphere. This describes cylindrical symmetry, correct? And the electric field here is a constant, so I can take it out, just like that. Oops, just let me draw it a little bit better. There we go. And this is dA equals Q enclosed over epsilon naught. Okay? All right. By the way, I forgot to mention something. Let's assume that the problem said, and I think the problem in the 24.5 said it, the electric field, there we go. He said we use the superposition. He said the charged wire of linear charge density lambda. In other words, he didn't tell us it is charge, the charge on the wire is big Q. It has a linear charge density lambda, okay? So it has a linear charge density lambda. In other words, we're making the problem just a little bit harder. Not Q enclosed, as I said here, the formula says enclosed charge, but the problem says the charged wire here has a charge density lambda, okay? All right. Now, you agree with me that this dA is the surface area of what? Of the Gaussian cylinder. And that's equal to what? What's the surface area of the cylinder? It's equal to 2 pi RL. For a cylinder, again, go back to your geometry. If I have any arbitrary cylinder, of radius r, the surface area of it, let's call it S, is equal to 2 pi r L. L is being the length of the of the cylinder, okay? And of course our Gaussian surface here is a cylinder, so I'm going to use this formula for dA, this one. You got it? So in this case, I can say that E times 2 pi r L equals Q enclosed over epsilon naught. So far so good? Okay. Again, he didn't mention anything about enclosed charge. He told us, he gave us information about just the linear charge density lambda. Okay? So what does that mean? Well, what that means, if you remember, what does lambda equal to? Lambda equal to the charge per unit length, L, for example, right? So for our case, so Q here is equal to lambda big L, L being the length of the cylinder. So now I can replace this Q enclosed with lambda L. So my expression here becomes E 2 pi r L equals to lambda L over epsilon naught, and if I solve for E, is equal to lambda L over epsilon naught times what? Times 1 over 2 pi r big L. As you can see here, the length, what am I doing? The L's cancel out, which is really interesting, over 2 pi epsilon naught times 1 over L. And there we go. I just solved the problem. Now, I have a comment to make before I move on, and that is, what's the meaning of the fact that the L's cancel out? Look, the problem says, find the electric field due to an infinitely long line of charge, right? And what I've done, I had a finite length cylindrical or Gaussian surface. Guess what? Even if I draw it even longer, it doesn't matter because the length L will get a cancel anyway. Do you see the trick? See, there is no length here in the expression. So basically, I solved the problem. Here it is. So this one, this expression describes the electric field of a cylindrical, or a line of charge of any length, whether it's infinite or not. You will get the same expression regardless of how tall the cylinder is or how long the wire is. That's what's interesting about this expression. And by the way, we have encountered this expression back in chapter 23. If you go back to example, and I think I told you to read it, example 23.3, on page 638 in the book, textbook, where he uses, if I remember Coulomb's law, to derive the same expressions, and he spends almost 2 pages of calculation to get that, and as we can see, we only did it in a few steps. Let me go back to the book and show it to you very quickly. I hope I'll get it very quickly. You know what? I'm going to cut the video. Okay, I am in example 23.3 right here. It says the electric field of a line of charge. Please take the time to read it. And so here is the line of charge right here. And in this example, he calculates the electric field, and he does it the way we did it in, if you remember, in chapter 23, where you put the x-axis here, and then you pick a point, and then you look at the electric field, and then you analyze the vector, x and y component, just like we did with the ring and the disk, and he does it for this line of charge. And then he goes on through the calculation. Here they are. He goes on and on and on. It's a very long page. Again, he keeps going with it, and then he comes up with this, and then here an infinite line of charge, and then he takes the limit of this final expression, and then he finally comes up with it right here. Okay, this expression is exactly the same as this expression right here, the one we got. But of course, as you can see, we did it in basically a couple of steps. I'm doing a lot of details here that are not necessary, but you can do it really in a couple of steps, and you end up getting this expression, which is the same as this expression right here. He just have a 2 and a 4. We had a 2 and a 1 and a 2 here, the same thing, right? But as you can see, you can just see how powerful and how elegant Gauss's law is in comparison to this method. You see what I'm saying? That's why Gauss's law is such a beautiful, beautiful way of calculating electric field, specifically for object with very high symmetry. Okay. The last example I want to do, and that is the electric field due to a plane of charge. Again, this is also done in your book. Example, I'm looking at my book here, 24.6. 24.6. Let me go back to chapter 24, section, what am I, section 5, 25, section 5 right here, and then examples, I'm sorry, 6. Trying to find it for you. Example 5, we just did that, and I think that's his answer right here. And there we go. He said the electric field of a plane of charge, okay? And then, again, he doesn't put the charge Q, he put a charge density, sigma. We use sigma, he uses eta, the Greek letter eta. I use the Greek letter sigma. He says, use Gauss's law to find the electric field of an infinite plane of charge with surface charge density eta, or sigma. Okay? Let's do that. Again, it's not a difficult problem, using Gauss's law, that is. (24.6) electric field of an infinite plane of charge. This one is interesting, and please pay attention to how it is done, because it becomes useful when we cover capacitors. Anyway, so what we have here is an infinite sheet. Imagine you have an infinite sheet. I'm trying to erase this dot. There it is. So I have here's an infinite sheet. I'm trying to make it 3D as much as possible. Let's make it rectangular, but it is, again, it's infinite. So it extends all, very, very in all directions. And it is, let's assume it's positive all over like that, and so on, okay? And I want to find the electric field due to it. So what you do, again, you find a trick to do it. Remember, we always insist that the Gaussian surface have to be closed. There are no holes in it, okay? So I can't say, oh, imagine let's say a Gaussian surface where it is a sheet, because a sheet is not a closed surface. So that's not possible. So one way to do that is, oops, I'm trying to erase all that. Just give me a second. One way to do it, again, it's a trick. You imagine you have a cylinder. In older books, they call it a pillbox. Imagine you have a cylinder that is coming out of it like that. I'll try to draw it. Here is a cylinder that coming out of the surface of this infinite sheet, and it's coming from both sides. So it goes on the other side of the sheet like that. Okay? And this surface, or a pillbox, so in this case you will have electric field coming out of it like that, and this is our dA, if you will, right? And then from the other side, remember that's a sheet, so the electric field is coming out from both sides. You see what I'm saying? It's from both sides. So here we also have the same thing from the other side of the, so we have E coming out, and both of these E's are equal to each other, and that's dA, if you will, okay? Maybe I'll show you how it looks like in the book. Maybe the book has a better picture. Here it is, right here. So here you have an infinite sheet. I can't magnify it any more than that. That's funny. So anyway, here is the infinite sheet here. And then imagine a cylinder or a pillbox, a Gaussian surface that is. And so here you have the electric field in red and electric field in red. They're both equal. And then you have dA and dA, okay? Like that. Okay, so what does that mean? Well, okay. Let's go back to Gauss's law. Gauss's law says E dot dA equals Q enclosed over epsilon naught. All right. Now remember, what is, go back to the previous video lecture, part 1. What does that mean? That's the flux, remember that? That's nothing but the flux. It's just a fancy way of writing the flux. Now, since this problem is symmetric and simple, we don't need the integral. Basically, what that means is this. Well, let's keep the integral. Let me show you. Now, we agree that the electric field is the same here and here, so I can take it out of the integral, and I'm left, the same argument. So I have E integral dA equals Q enclosed over epsilon naught. Now, what does that mean? What is this? This one is nothing but the cross-sectional area of this pillbox, of this cylinder. This one right here. Well, what is that? Well, it's just pi r squared. Or, for simplicity, let's just call it R. A. Okay? For simplicity, let's just call it A. So in this case, it becomes EA, which is the flux, equals Q enclosed over epsilon naught. Is that right? However, I have two of them. I have one here and one here. So I have to add both. Okay? I have to add. So in this case, because I have two sides, it's really two of them. I have two areas here. This makes sense? That's the first thing. Second, what is the Q enclosed? He didn't give it to me. He said that the surface charge density is sigma. Well, we know that sigma is equal to Q over the area. So Q is basically sigma A. Now I go back and plug it in here. So I have 2EA equals sigma A over epsilon naught. The A's cancel out, as you can see. And I have E equal sigma over 2 epsilon naught. And this is the famous formula for the electric field due to a charged sheet, or to a charged infinite sheet. Okay. Again, I believe I talked to you about it when we covered the previous chapter. Let me show you the example that I talked about. And I'm going to take you back to chapter 23, page. Go back to chapter 23, page, I'm looking at my book here, 642. I'm going to take you there. I already got there. Here is the plane of charge. You see that? This is page 642 of chapter 23. And if you look at it, he doesn't really derive it for it. He just kind of put it right there and tell you, here it is. Remember, I think I told you about it, and there it is right here. So the electric field due to a plane of charge is that, but he did not derive it because you really need the concept of the flux and Gauss's law to derive it. And we were able, so equation 23.28. we have the same formula. Okay. One more comment about this formula that is important for us when we cover capacitor, so I'm going to get it over with and explain it here, is the following. I think I told you a little bit about what capacitor is. Imagine you have two metal sheets. One is positively charged and the other one is negatively charged. And then they are very, very close to each other. So here they are. Here is one metal sheet here. Again, this is just a two-dimensional picture of them. Let's make this positive. And here is the other one, negative, like that. Oops. Trying to make it as straight as I can. Like that, okay? And now if I ask the question, okay, as you know, the electric field is going to go like that. From positive to negative. This is the electric field. And if I ask the question, what is an expression for the electric field inside? What is the mathematical expression for this electric field that describes this capacitor? Okay. Now remember, the distance between the two plates is extremely small compared to their dimension. I'm talking in the order of, say, micrometer or a fraction of a millimeter. Okay? Well, the drawing doesn't give it justice, but it's really, really tiny. You can hardly see the difference. Basically, it's less than a thickness of a sheet of paper. Okay, the separation distance between the plates. Okay, but here's how it works. Watch. If I pick a point outside, okay, so if I think of each plate as a infinite sheet, or, you know, a sheet like the one we just covered, okay? So let's look at the positive sheet. I want to know what is the electric field due to this positive sheet here at this point, okay? So it's going to look something like that. The electric field is going to be, sorry, let me call this sheet number 1, and this is sheet number 2, just for simplicity. So it's going to be E1 is going to be this way, and then E2 is going to be in this direction. And because E1 and E2, or the plates are really close to each other, basically they're going to cancel each other out. Okay. Now if I go here and put a point, the same point, E1 is going to be in this direction, away, right? And then E2 is going to be towards it, and they're both equal and opposite, so they're going to cancel each other out. In other words, the electric field here, the net sum, is 0, and the sum of the electric field here is 0. But watch what will happen if I put the point here. Okay? So what's going to happen here, due to the positive plate, it's going to be like that, right? And to the negative plate, it's going to be like that as well. Let me take that out. There we go. It's going to be this way as well. You see that? In other words, those two are going to add up together. So the E net here inside, sum of the electric field inside, is just going to be E1 plus E2. Ignore the minus sign. Going to the left. Just ignore it. We can switch the polarity and you'll have a positive. It doesn't matter. So, but E1 is equal to what? E1 is equal to this. And E2 is equal to this one. So now I'm going to add them up together. So that's just going to be sigma over 2 epsilon naught plus sigma over 2 epsilon naught. And so it is sigma over epsilon naught. There we go. So the electric field inside a capacitor is this. We're going to be dealing with this formula later. Okay? That's why this last example is interesting, because it actually gives us an expression for what is the electric field inside a capacitor. Well, here it is right there. And we have just derived this in a very, very simple way. Very simple and elegant way, because thanks to Gauss's law. Got it? Good. All right. Here is a problem from the homework. I have at least one to do. Problem number 34. It's not very difficult at all. Let me go to the book. Oh, the book, the e-book. 24. 34 questions. There we go. Number 34. There we go, right here. Okay. Says a spherically symmetric charge distribution produces the electric field E equals 5,000 r squared in the radial direction. This is our unit vector, right? Okay, that's just a unit, Newton per Coulomb. So 5,000 r squared. It's not an inverse square law. It's actually r squared. It's like a quadratic. In the radial direction, where r is in meters. Okay. A, B, and C said, what is the electric field at r equal 20? Well, that's easy. Just plug it in. You're done. Right? B, what is the electric flux through the a 40 centimeter diameter spherical surface that is concentric with the charge distribution? In other words, draw a Gaussian surface of 40 centimeters, diameter of 40, and calculate the flux of that. And then C, he said, how much charge is inside the 40 centimeter diameter spherical surface? All right, let's do this problem. I'll put it on the side like that. Okay, so how do we do it? Well, we have here this expression. I don't need to draw anything really. So what's given to us is E equals E vector is equal to 5,000 r squared r unit vector. Okay, I don't like putting units on expressions. I'll just put it way back there. I don't need it. Anyway, there we go. So part A, he says, what is E at r equals 20 centimeter? Simple. All I need to do is just plug it in. Of course, in meters. So is this going to be E? Keep it in. Well, we can put the vector component to it. I'm not sure how your mastering wants it, but anyway, you can find out. So that's going to be 5,000 times 0.2 squared, right? R unit vector, and then you just calculate that. So 0.2 squared multiplied by 5,000, and now I'm going to get 200 r unit vector Newton per Coulomb. There we go. Simple. Okay. Part B. He says, what is, go back to it again, what's the electric flux, phi, what's the electric flux through a 40 centimeter diameter, which means radius 20, same thing, spherical surface that is concentric with the charge distribution. All right, so the flux, as you know, is EA, okay, in the simplest form, and I already calculated E's right here for that radius of 20, so all I needed to get the area. Well, the area, I'm dealing with a sphere, so that makes it 4 pi r squared. So that's going to be 4 pi. And r here is 0.2. Why 0.2? Because he said the diameter, 2r, excuse me. 2r is 40 centimeter. That's the diameter. So the radius in this case becomes 20. And then you convert it to meters. So 0.2 squared. And so the area in this case becomes, if I calculate that, 0.5 meters squared. Okay, so therefore the flux is equal to EA. I already have E's right here, and here's A. Becomes a trivia problem, so it's just going to be 200. Multiply this by 0.5, and that will give me 100 Newton meter squared per Coulomb. Okay? All right, part C, how much charge inside it? Okay, how much charge? Well, how do you do that? How do we get the charge? He said, how much charge inside? So he wants that. How do we do it? Well, what is the flux? The flux is EA, right? Which what we got just now. Well, what does the flux equal to? Remember? The flux has, here is Gauss's law. Go back to Gauss's law. Right? This is the flux, correct? Well, this is equal to it, so that's also a flux. In other words, there is another expression for a flux, is the enclosed charge over epsilon naught. Remember, this is EA. Well, this EA is equal to Q enclosed over epsilon naught. So he said, what is what is the Q enclosed? So that's just Q enclosed over epsilon naught. Therefore, Q enclosed is nothing but epsilon naught EA. There we go. Make sense? Okay. So when you plug it in, just plug it in. So you have epsilon naught is 8.85 times 10 to the negative 12. And of course, I already got that right here. Oop. Right there, right? So now I go back and I will get my 100 here. And then when I calculate that, it's going to be 8.85 times 10 to the negative 10 Coulomb. And there we go. That's how much charge enclosed in there. Okay? Okay, good. You know what? I'm going to do one more. I am not sure if it's homework. This is kind of a toughy problem. It is problem number 55. I always enjoy doing it in lecture. You know, back in the old days when we met in person, I always enjoy doing it. My background is in particle and nuclear physics, and I like those kind of problems. This one is an actual problem that I've learned when I was taking a course, my first course in nuclear physics. It actually was done by Arthur Rutherford. He's considered the father of nuclear physics. He got the Nobel Prize in 1923 or something like that for discovering the nucleus of the atom. I mean, he's the one who said that atoms must have nuclei in there. He's the one who discovered that with his famous experiment. And then he created a model for what is the electric field of that nucleus, of the atom inside. And he used Gauss' law to do this problem. Very, very interesting problem. Anyway, I'm going to do it. Let's do it very quickly. It's number 55. One of the reasons I like the book, about this book, is the fact that it has really, really nice problems, collection of problems. So I'm in 24. Oh, I was reading. I'm in 23. Let me go back to the problems here. 55. I need to go to the hard copy as well. There we go. Okay, let's read it together. It's level 3. It's a challenge problem. It's not an easy problem, but it's a really beautiful problem. He says an early model of the atom proposed by Rutherford after his discovery of the atomic nucleus. He's the one who discovered the nucleus. He said it has a positive point charge. What he said when he discovered it, he said there have to exist a central massive object inside the atom, and that massive object is positive. And then they get a smear of negative charges surrounding it. He didn't know the electron yet. It was his student, Niels Bohr, who gave the atom the solar system model, where you get the electrons going around the nucleus. That's a solar system model. And that was Niels Bohr, and I believe he got the Nobel Prize for it as well. But of course, it turned out that he was wrong with the birth of quantum mechanics. All of that was not terribly accurate, but not terribly wrong. I mean, he said a lot of. We still use Niels Bohr model of the hydrogen atom. Anyway, so an early model of the atom proposed by Rutherford after his discovery of the atomic nucleus had a positive point charge plus Ze. Z is the number of protons in there, right? E is the fundamental charge. The nucleus at the center of a sphere of radius r. Okay, that's the center of radius of the atom, with uniformly distributed negative charges. Okay, he didn't know the electrons yet, so he said there is a smear of negative charges surrounding it. Negative Ze. See, they have the same charge, EE, but except that the proton and the electron, they have very different masses. The proton is much more massive, but they have exactly the same fundamental charge, E. Okay, Z here is the atomic number of protons. the nucleus. Okay, so he said there are three parts. The part B and A are kind of easy. It's part A is the hard one. He said show that the electric field strength inside this atom is given by this expression. Okay, all right. So we're going to be using what we studied to derive this expression. Okay, this is actually how we did it. So let's see how we did it. It's not terribly difficult, but it's not terribly easy either. Anyway, so problem number 55. Okay, first, it's very important that you draw the free body diagram, because in order for you want to see the picture, how it looks like. So here is the classic atom of Mr. Rutherford. There's a big giant atom like that. Okay, and then there is this massive positive central mass. This is his language using it. Positive central mass. And then surrounded with a smear, if you will, that's just my word, of negative charges there. And these negative charges, negative ZE. Later on we knew they are electrons. But anyway, here it is. And of course the radius of this atom is big R. Okay, it's a constant value. So far so good. Later on it will be called the Bohr radius. He was measuring it, 5.29 times 10 to the negative 11. This is for the hydrogen atom, for example. It became a magic number. Anyway, so there we go. And we want to know, let's go back to the problem again. He says, show that the electric field inside is given by this electric field. Inside. So what we have in here, does this remind you of something? Well, it reminds me of the non-conducting sphere. Remember, we said that the non-conducting sphere has the charges inside distributed uniformly. There it is. We have the same thing. So if you understand the example that I have just worked out, you shouldn't have a problem understanding the step that I'm going to go through to derive this expression that he just showed us. Okay, here's how we do it. Let me try another color. So let's try green. So what I'm going to do, I'm going to draw a Gaussian surface inside. There it is. This is the Gaussian. Let's make it just a solid green like that. That's a Gaussian surface right here of radius small r, right? The variable. There we go. Okay. Okay, so for r less than r inside, we're going to use the same thing. So before I do anything, what is the total charge inside the enclosed charge? Let's talk about that, the enclosed charge. Well, inside the Gaussian surface, obviously I have a nucleus. And the nucleus charge is plus ZE, right? So I have that, no problem. That's for the nucleus. Plus what? A fraction of negative ZE. You see what I'm saying? A fraction of it. What's that fraction? I don't know. But it's a fraction. You agree with me on that? So it's a fraction of that. Well, how do I find that fraction? Remember we did that. If I call this negative ZE, let me call it negative Q enclosed. Okay? I'm just coming up with some notation. There it is. Well, what is it equal to? Negative, call it prime, because I don't want, this negative. I want to resolve this one for the full charge, the total charge, but this one is that. Well, what is it equal to? If you remember, we said that Q is equal to rho V, correct? Where V is what? The volume of the Gaussian surface. So I can write this is in this form. Watch. I have that. This is the easy part. Plus, I got rho V with that minus because there are minus charges in there. So allow me to just put that minus right here once and for all so I don't have to deal with it again. Trying to erase this darn thing. There it is. My pencil is not, it's acting up. There we go. So I have this minus rho V. Okay. V here is what is the volume of the Gaussian surface. So ZE minus rho, well, what is the volume? 4/3 pi r cubed, small r. So far so good? Okay. Next, I am trying to get rid of this rho. I'm not interested in this rho. Now let's look at the whole atom, the whole thing. What is rho in terms of that? Well, rho in this case will be, remember, the whole atom is of radius big R. So the charge density in this case is going to be minus ZE over 4/3 pi big R cubed. Make sense? So now I'm going to go back. I'm going to put this thing right there. Now I am putting two minuses. I mean, I meant this minus is the same as this minus. Maybe I should, let me just keep that plus here. I'm sorry about that. I hope you're not confused with that. It's got to be one minus. So anyway, so we have that. So it becomes plus ZE. That's for the nucleus. Plus, now I have this one. Minus ZE over 4/3 pi r cubed. This is the charge per volume for the negative charges times 4/3 pi r cubed. Of course, those cancel out, and I end up with ZE minus ZE, and I have R over big R quantity cubed. That's the charge enclosed. There it is. I'm not done yet. I'm just derived that. Now he's asking for, let me go one more step. Let me take ZE as a common factor. So in this case, I'm going to get ZE bracket 1 minus R cubed over R cubed. That's the charge enclosed. I like this expression better than the one above. Okay. All right. Now, let's go to Gauss's law. I have an expression for the charge enclosed. That's silly. I'll put that epsilon here. Okay. I have this expression right there. And of course, as far as Gauss's law is concerned, well, that's just E and then 4 pi r squared for the surface area. We already made those arguments several times, equals to charge enclosed over epsilon naught. And then now I just need to solve for E. In this case, it's going to be 1 over 4 pi epsilon naught 1 over r squared times the charge enclosed, and it is this one right there. I'm going to put it right here. Whoops. And that's going to be ZE bracket 1 minus r cubed over big R cubed. Now I want to insert this r squared in there, and therefore the electric field is going to be, just clean it up a little bit, ZE over 4 pi epsilon naught 1 over r squared minus r over r cubed. And there we go. I have an expression for the electric field, which is the same as that. See that? Got it? Okay. The next question, he said, what is E at the surface of the atom? Is this the expected value? Well, before I do it, I'm going to ask this question. What is the value of E at the surface of the atom? What do you think? Well, it should be 0, because we know that atoms are neutral, right? If atoms are neutral, that means right outside the atom, things are going to cancel each other out. Well, let's prove it. I mean, this is one way to prove if the Mr. Bohr's model, the Bohr model, the Rutherford model of the nucleus or the atom is correct. So at surface, that means R equals big R. So all I need to do is to replace small r with big R and see if I get 0. ZE over 4 pi epsilon naught 1 over r squared minus r over r cubed. Obviously, you're going to get 0, right? And there we go. So it's 0. Is that the expected value? Yes. Atoms are neutral. And then part C, I'm going to let you do it if you want to do it. Just the numerical, you just want to plug in some numbers in there. He says a uranium atom of Ze92, excuse me, the number of protons Ze92, and the radius is 0.1 nanometer. What is the electric field at R equals half R? You can just plug it in and get the number. So I'm sure you can do that yourself. Okay, and I think I'm going to, I'll give you the answer if you want it. The answer, I have it in my notes here. 4.6 times 10 to the 13 Newton per Coulomb. Okay, that's it. I think I'm going to stop here. You have a wonderful week. Bye-bye.